Welcome to the House That STEM Built, a regular series where we will explore the science, technology, engineering, and math that goes into the design and construction of this family home. This is the House That STEM Built.
Today, we will look at the science behind torque. Torque is a twisting and turning effect that results when the force is applied to an object that can rotate or spin around a central pivot point known as an axis. The amount of torque generated depends on how much force is put into the rotating object and how far away from the pivot point the force is applied. This video will address the Physics 12 Specific Curricular Outcomes ACP-1. Use vector analysis in two dimensions for systems involving two or more masses, relative motion, static equilibrium, and static torques.
Torque is the result of a force applied at a distance from the pivot point. These two factors are related in the formula tau equals F times R, where the Greek letter tau represents the amount of torque in units of Newton meters. F is the applied force in newtons, and R is the radius or distance from the pivot point the force is being applied in meters. Another factor in the amount of torque generated is the angle at which the force is applied. Any force applied that is at an angle that is not perpendicular to the radius will reduce the amount of torque generated. So we will only discuss forces applied perpendicularly for simplicity.
In the real world, there is rarely just one force acting upon any given object. To help understand what is going on, let's take a look at a simple example, a seesaw. Let's say you and your friend are sitting at opposite ends of the seesaw. If you both weigh the same and are sitting the exact same distance away from the pivot point of the seesaw, then what happens? The seesaw doesn't move. This is because the net torque is zero.
This doesn't mean that no torque is being applied to the seesaw, but rather the torque that you are applying in one direction matches the torque your friend is applying in the opposite direction. When the net torque is zero, it is called static torque. Nothing is moving because all of the individual torques sum up to zero.
But what if you and your friend weigh different amounts? Is there any way to achieve static torque then? We know that torque is a function of the applied force and the radius. So if the force on one side increases, what must happen to the torque to remain the same? There. Now the torques are even again.
But what happens if you want to move something? Say, a screw or a piece of wood? This would require dynamic torque. Dynamic torque occurs when the net torque is not equal to zero. Let's take what we've learned and apply it to the construction of a house.
Let's take a look at some examples of changing the force, but not the radius. When using a screwdriver to drive or remove a screw, you can easily get the job done, but sometimes it can be tedious and slow, especially if you're doing this over and over again. This is where a drill comes in.
By increasing the applied force, drills can apply a much greater torque on a screw, making the job quick and easy. There's another type of drill called an impact driver, and they can deliver even more torque. If you've ever tried to loosen a really tight bolt with a wrench and haven't been able to get it off, your next option may have been to hit the wrench with a hammer to deliver a sudden impact to loosen the bolt up. This is the same principle with impact drivers. They deliver repeated blows to deliver more torque to the screw you are driving.
Let's take a look at the screws themselves. The most common screw heads you'll find are the Phillips, Robertson, and flathead, or slotted. Each shape has its distinct advantages and disadvantages in the terms of helping to apply a torque to the screw. The flathead screws have been in use for a long time, but carpenters have had difficulties with them as the drivers they use kept slipping out of the slots too easily. The Robertson head was then invented by Canadian P.L. Robertson to prevent this from happening. Its deep squared-shaped socket allows drivers to apply a tremendous amount of torque to the screw without the driver popping out of the socket or disengaging.
In comparison, the Phillips head was made with a much shallower cross-shaped socket. This limits the amount of torque a driver can apply to the screw, as the driver will disengage at a certain level of torque. Since the invention of these famous screw heads, several other designs have emerged. Notably, the star-shaped Torx head was invented to maximize the amount of torque that could be applied to the screw, as many tools nowadays have torque limiting and torque accurate controls. The task of restricting torque is then no longer the screw's responsibility, but rather the tool's.
Next, let's see what changing the radius does to our torque. If you've ever tried to close a cupboard door by pushing it very close to the hinges, you know that is much harder than if you were to push the door as far away from the hinges as possible.
This is why tools like wrenches have such long handles. You can apply more torque to the object you are trying to loosen or tighten without having to apply more force, just by increasing the radius.
Torque is such an intuitive concept for construction workers that most of them use the principles of torque to their advantage without thinking about the theory behind it. A good example of this is the use of a pry bar. If you wanted to remove the nail that was sticking out of the piece of wood, you wouldn't want to try pulling it out with your bare hands. You would be applying a force to the nail that isn't big enough to overcome the force of friction that is holding that nail in the wood.
Instead of applying a force directly to the nail, you can apply a force to a pry bar, which is applying a torque on the nail. That long handle will allow you to apply a reasonable force, and just by increasing the radius, you will be able to apply greater torque to the nail. The large radius with a smaller force is able to overcome the small radius with a larger force.
Pry bars are used in a variety of situations as well. When screwing down deck boards, the builder of the deck wants the boards to be evenly spaced the entire length of the board. However, not every board is perfectly straight. To compensate for this, the builder will use a pry bar to bend the board so that it's touching a spacer at the point where they will screw it in. This is called persuading the wood. If you were to try to do this by pushing on the board, it would be very difficult. But by using a pry bar, the task is made much easier due to the long handle.
Some other examples of dynamic torque include the use of wrenches, gears, crank open windows, and fans. Can you think of any other examples? What would increasing or decreasing the applied force do? What about increasing or decreasing the radius?
As for static torque, there are plenty of applications as well. While dynamic torque may seem more useful for moving and dislodging objects, static torque is important for keeping things that we wouldn't want moving in their place.
For example, a ladder that is leaning on a wall is kept in place because all the forces acting on the ladder work together to create a static torque. Between the forces of friction on the ladder from the ground and the wall, the force of gravity acting on the person who is climbing the ladder, and the normal forces pushing back on the ladder from the ground and the wall, the ladder is kept firmly in place so it doesn't slide out from under the person climbing it.
However, ladders do slide out from underneath people from time to time. So why does this happen? How can we keep this from happening? What are the limitations of the system? What if the floor and the walls were really smooth and therefore had smaller coefficients of friction? Would the person's weight make a difference? What other factors play into this situation?
In this video, we learn what torque is, what factors play into it, and how they affect the amount of torque overall. We learn the difference between static and dynamic torque and how each one is used to the advantage of construction workers when building a house.
We also learned about several tools that were designed to help us take advantage of torque. What are the other areas of the construction of a house that require thought given to torque?